I still have a couple of minutes, so I thought I'll scare you a little bit with this. Has anyone seen this before? Tacoma Narrows Bridge, yeah, in the 50s. So this is a prime example of what's called vortex shedding, aerodynamic induced instability. So as flow is crossing the bridge from the other side to this side, it's fairly uniform, and then it hits an obstacle. What happens, it creates an oscillatory flow behind the object. So this happens on like things that have square cross-section, cylinders, airfoils, anything. So you get a bunch of alternating vortices behind on the other side, and those change direction due to pressure gradient oscillating. And so this is an example of this causing a disaster. There's a well-known disaster, and you're going to model this in your homework assignment. So we're going to take a small angle, and we're going to put an oscillatory wind. And when I taught fluids, I had my students derive the system of equations for this, etc. You're not there yet, but I'll give you those equations. It's a simple spring mass damper system. Well, not very simple, but yeah. And then you look at amplification. So if you have a small angle of initial angle, like almost 1/1000th of a radians, and then you put this flow around it, it's going to amplify 100, 200 times, and then eventually it will crash. Okay? So this is not a question if you like this on the homework. It's going to be either on your homework or on your project. So it will be on your homework. The project 2 will be something else. Okay? So, but we're studying to solve these equations, and it'll be good. Okay. So we will get back to our baking Mr. Lobster. I guess for YouTube, I have to say, let's begin. I have the cue. Let's begin. Last time we left off, we were boiling and baking Mr. Lobster in our Jupyter notebook. So if you were to open the Jupyter notebook, I think this was still running here. We solved the heat equation for the temperature of the lobster as a function of time. So on the y-axis, I'm plotting the temperature in kelvins, and on the x-axis is the time in minutes. So you have boiling water in black, and oven, radiation environment in red, and these curves represent the temperature of the lobster as a function of time, right? So at t equals 0, they're both at the same room temperature. Then after 2.5 minutes, in boiling, it's almost reached 375 degrees, and then it stayed flat because it cannot heat it anymore because T infinity, we've reached T infinity. Whereas for these settings that we had, the radiation took a little longer, about 12 minutes to reach that same temperature. So that's analyzing the physics, but computationally, this doesn't look really good. This doesn't look like it's accurate, although it has control over the error. It is a stable solution. It's not exploding. It's giving us reasonable temperatures, but I don't. It looks too sparse, too coarse. It doesn't look like it's putting enough time points in between in this interval for 20 minutes. It doesn't look like it's putting enough time points. Remember, for solve IVP, we only had to give it a time span, T0 and T final, and solve IVP is going to automatically pick the time points for you. How does it do that? I said last time, it's magic. It's not magic, it's mathematics. Internally, it's doing some internal dynamics where it's calculating stability and estimating, trying to keep the error bounded and estimating what the next step should be without the solution blowing up. There's a lot going on if you dig into the details, but it's nicely doing all of that for you. However, for you as a user, and obviously you don't want to be an expert in time integration or what is going on behind the scenes. You just want to use this. You just want to know enough that you don't get yourself in trouble, right? And So the next step for us is to figure out what parameters can we pass solve IVP to get a slightly more, to get more points, if you want, more points in the time domain. Okay, so let's look at that. There's two options we can do this with. The two approaches are options that we pass to the solver to solve IVP. And the first one is called dense output, enabling what's called dense output. And the second one is specifying the time points at which you want to get the solution. Both of these options are similar in the sense that there's some advanced mathematics where you can solve a differential equation at specific points, which the solver is choosing, and then build interpolating polynomials between those points, like splines. It's a little bit more involved because it uses the differential equation itself to build those approximations, but it provides you with a nice, smooth, continuous solution. Okay? So we will start with dense output. With dense output, we will start, I guess, with t-eval. Okay, we'll start with t-eval, which is easier. So this is an option that you provide in solve IVP. And t-eval is nothing more than a linear space telling the solver, I want you to find me the solution at those time points. Now, internally, it's not necessarily solving the system of equations at those points. It might be approximating it, but it will give you a solution at those points. So what we would do in this case for the lobster, we are going to provide about 100 time points or 200 time points between 0 and 20 minutes, right? And we will pass this to solve IVP. Now, be careful that your t-eval array of times, it needs to start at t0 and end at t-final. You cannot go for less points or more points. Okay, it needs to be bounded by those two. Okay? And then you specify how many points you want. So in this case, what I'm doing, I'm creating a new space for the dense output, and I'm saying for t-eval, I'm saying create a lint space of 100 points from t0 to t-final, and then pass this as a property as an argument in the integrator. So let's do this in Python. So I'll create a new cell here so that we get to compare. Okay. So, and then here we're going to go here. We're going to see more time points using t-eval. Okay. So I'm going to copy this. Again, I'm showing you now the methodology of solving the problem, and your purpose is not just knowing how to use solve IVP. Your objective is to use solve IVP effectively to analyze this problem. So your purpose is always the physics, not the numerics. Okay? Although the numerics are fun to think about and to know. All right. So what we will do here, we'll create a t-span or t points, time points, call it time points, mp.lint space going from t0 to t-final, and I want to put 100 points. And over here, you go to solve IVP, you put the cursor next to the parentheses. If you press Shift-Tab, oh, hold on, let me run this again. Come on. Okay, I might have to restart my Jupyter Notebook. Give me a moment. Nope, it's good. Okay. Radiation, solar radiation. Okay, so this is still valid. Now, if you go here on Solve IVP and press Shift-Tab, you see here these options are necessary. Everything else is optional. How do you know that an argument is optional? If it's provided a value by default. So here, method is provided a value by default. T-eval is none. We want to say, no, we're going to provide t-eval in this case. Dense output, etc. We're going to learn about all of those throughout these few lectures. But I'm looking now at t-eval. So if you scroll down to t-eval here, parameters, function, t-span, y0, method, etc., etc., You go to eval array like. These are the times at which to store the computed solution must be sorted and lie within t span. So it could be between t0 and t final. It cannot be outside t0 and t final. So it could be a subset of t0 and t final. I think I said it has to be between, it can be anywhere between t0 and t final. But let's just take it from t0 to t final. And what we will do here is t eval equal time points and t eval equal time points. Bless you. Okay. So now we want to plot this, but what do you plot it against? Do you plot it against time points or against solution.t? If you remember, sol.boiling.t gives us all the time points, okay, that at which this was computed. So you should always plot against sol.t, okay? So let's copy this and paste it here. Now we should have a much cleaner plot, maybe without the symbols. Okay, you get something like this. Okay? Now here it has these small oscillations. This is something that started showing up with Solve IVP, but don't worry about those. They're stable oscillations, and I think this has to do with the integrator picking these sorts of type points. We have control. We can have control over that. I'll explain that later by telling it to specify a certain error tolerance, for example, or a certain maximum time step size. But this does the job for you. Okay, this does work, providing these. You could put 200 points if you want, and you're going to get the solution. It's not going to get any smoother. Okay, so the next option. This is t-eval, one way to get more solution at more time points. The next option is called dense output. Dense output, you can either use t-eval or dense output. Okay, dense output, you just turn it on, say dense output equal true. What it does, it still computes at the points it wants to compute at, but it also builds a dense output. It builds an interpolating polynomial from t0 to t final. And then you can evaluate your solution anywhere between those points. So it's going to work a little differently. What you do, once you turn on dense output, then you create a dense linear space and time anywhere between t0 and t final. Okay? And then you call the solution. Within the solution, there's an object called sol. So here I had sol.sol because here I called it sol. Okay, so or solution boiling.sol. So this sol object, if you give it an array of time points, if dense output is turned on, it will evaluate it at all of those points using interpolating polynomials. Okay, so let's try this again. So more time points using dense output. Okay, so now I'm actually going to copy this and paste it here. But now I don't have t-eval. I have dense output equal true. And dense output equal true. Okay, so now if I'm back here and I plot, I'm going to plot these. What do you think it's going to be? It's going to be the old method, right? Because we didn't say evaluated at t-eval. We just turned on dense output, which turns on interpolating polynomials between these points. But the solver is still solving at the points it wants to choose. To access the dense point solution, then what you would do is create a linspace, t-dense, let's say, mp.linspace from t0 to t final. Let's put 100 points. And then you want to access the dense solution. So solution, sol, dense, boiling. That's what the boiling is going to be sol boiling, which is this guy, sol boiling, and from that object I want to access sol. Okay, so if you look at solve IVP, what it returns, if you scroll down here, it's going to return an object. It contains this. This is what I'm trying to access here. This is the solution that allows you, if you had dense output on, you can use this object here to evaluate your ODE anywhere between T0 and T final. Okay? So you access it by accessing your solution object, which is sol boiling in this case, and from it you call sol, and then apply it at T dense. And same thing for sol dense radiation. It's sol radiation dot sol at T dense. And now if I want to plot, now I'm plotting the dense solution versus the T dense array. Okay? Oops. I'm not using the sol radiation or sol boiling dot T because those are still the sparse points over here. And then sol dense boiling. Okay. And I think this is going to throw an error because, I'll tell you why. Okay. So let's print sol dense boiling. If you print it, you see it's an array of an array. Okay, so I need to access the inside array, so I have to put a bracket 0 to access the internal array. So if I put sol dense boiling 0, then it gives me just the one array. So here I need to plot 0. This is the case because when you have a system of equations, the dense solution is going to return an array for each variable. So you're going to have an array of arrays. Okay. And so we plot this now. You see this dense output solution that looks more continuous. It's still not solving the ODE at the intermediate points. Same with T eval. It is choosing its own points. It wants to choose those points on its own, but it's doing some kind of interpolation in between. Okay? So it's not creating new information. It's just interpolating between existing data points. This is not the most accurate way, but it does a pretty good job. Okay? We will see other ways later when we get to stiff systems and more highly nonlinear systems. Okay, are we in sync? Do you want me to move up a little bit here to see what we've done?
So what's the benefit, or which one?
They're the same. They're the same, yeah. I like the dense output because it provides me, it doesn't lock me into, so once you have dense output, I don't have to rerun the solver again with a different T eval interval. I can just evaluate the solution object with any T dense array. I could put 1,000 points here and still evaluate it from the single solution. I don't have to run solve IVP again. Does that make sense? So let's say I want to do 500 points, but between 5 minutes and 7 minutes. With the other method, you have to rerun solve IVP. Agreed? You have to run it again. With this one, no. You already have a dense output solution, and you just apply that dense output to an arbitrary subarray or array. So I like that option better. They're technically doing the same thing. Okay, so you're not getting any benefit either or. Dense output is the one I would recommend. Okay. And so you can do this and you can get a nicer solution. Then you can investigate the cooking or baking. You can play with the parameters and see which one is going to be faster. You're going to cook it in 2 minutes. By the time the person makes the order and they're out, and you can figure that out. You can play with the heat transfer coefficients, etc. So that becomes the physics problem where you as an engineer needs to figure this out. So I put this out here. This is the object that is returned from solve IVP. This is sol that we just used. I want to point your attention to this. We're going to use this a little later, hopefully today, if not today, on Tuesday, that the solution object has information about the solution, like information about the error and other things like that. One of them is this NFEV, number of function evaluations. So this is a very important metric that we will use later to estimate the cost of solve IVP for when we're using different methods. That's going to be very relevant as we get to stiff systems, and I explain stiffness, but we're not there yet. I just wanted to point that out to you. Okay. Not ODE int, sorry. Solve IVP, I'm still living in the past. Solve IVP, just like root, solve IVP also allows you to pass arguments to the right-hand side. There's no need to discuss this again. We know how to use it. If your right-hand side routine, which should always be right-hand side t comma phi or t comma dependent variable, and then it has a bunch of other arguments, you can pass them through this with args. You can pass the arguments, and they will get passed on to your right-hand side. So this is also a typo here. My apologies. So this t phi. So yeah, if your right-hand side looks like this, then you can pass those additional arguments from solve IVP. This can become handy when you're running, when you don't want to declare global variables, which you shouldn't. And as you pass parameters along, let's say you're changing the emissivity in the radiation right-hand side, for example, you would pass the emissivity as an argument from solve IVP. No, you don't have to go and change it every time in the right-hand side equation, in the right-hand side routine. Okay. Next, we want to talk about systems of ordinary differential equations. There are two general ways where systems of ODEs arise, and so far we've talked only about first order ODEs, initial value problems. I'm focused on IVPs, so initial value problems. When you have a second order initial value problem, third order, fourth order, and so on, there is no direct mechanism in Python to solve a high order IVP. Instead, what we typically do, we do what's called order reduction. We convert higher order ODEs into systems of first order ODEs. We do have the tool that solves a first order ODE, and it's called solve IVP. And there's a very simple trick that you can use to convert any high order IVP. So when I say ODE, we're still operating in IVPs. You don't do this for boundary value problems. You do it for initial value problems. So we can convert a second order IVP into two first order IVPs. We can convert a third order IVP into three first order IVPs, and so on and so forth. It's a very common technique that this way we standardize. The beauty of this is that you only need one routine called solve IVP to solve systems of first order ODEs, and any higher order IVP, you can convert it into a system of first order IVPs. So you'll always use solve IVP, and that's pretty effective. So that's one place where systems of initial value problems arise. Another one is actually some mechanisms, like reaction kinetics is a classic example, epidemiological models, and in chemistry, a lot of ways you will end up with systems of initial value problems. Okay, the example I gave last time, which we will get to later today, is the susceptible, infected, and recovered epidemic model for flu or COVID or any virus that's infecting people, etc. So this is an example of a system of IVPs that arises naturally. But first we're going to discuss how to do order reduction. I'll do one example with you, but I have 4 other examples in the slides that you can do on your own, 3 other examples. So it's customary to convert these higher order IVPs into a system of first order ODEs. So we'll start with an example. It's just a mechanistic process you apply over and over again. It just works. Here's an example ODE. This is like a spring mass damper system with some forcing. So the classic spring mass damper system, U double prime plus some damping. So this would be, if U is the position, for example, of the spring system, this would be the acceleration, this would be the speed, and this would be the damping term, and this would be the restoring force, Hooke's law, if you remember, Kx, K times the displacement, right? And this is a forcing where you're forcing the oscillations on the object. So this is a classic second order initial value problem. You're given the initial conditions you need two initial conditions here because you have a second order ODE. So the first initial condition is on the displacement itself. At t equals 0, the initial displacement is 1 unit or 1 meter, if you want. This should be dimensionless. Why should this be dimensionless?
Saying the sine function?
Yeah.
Well, sine can't take units in and it can't put out units.
Correct. Yeah, so if you just look at the balance of dimensions, you're looking here. A quick way to tell, just look at the terms. Are they homogeneous in their dimensions? And just by looking at sine t here, these functions are dimensionless. You can't put a number in sine and return something in length, in meters. It's meaningless, right? So all functions in math, they are dimensionless. You can only get units when you multiply them by a parameter, right? And so looking at this, because this is dimensionless, then everything else here is dimensionless. So I say here there's this 1 unit in distance. It's a dimensionless unit, but 1 unit in distance, and the initial speed is 0. Okay, so how would we do this to run it in solve IVP? First step is to introduce new variables for all the derivatives up to 1 less than the highest order. So here we have a second order derivative, but we have a first order and a 0th order. So I'm going to introduce 2 variables, one for this guy and one for u prime. So one variable for you, for me, for you, one variable for you and one variable for u prime. I've been messing with my son. He's doing like some coloring, and he would tell me there's like letters he has to color, and they write in the homework assignment, U is purple, for example. And he tells me, what color is U? I tell him me, and he laughs, so he thinks it's so funny. It's like, that's the best part of being a dad with young kids, daddy jokes. And then they become embarrassed with you from your silly jokes. Anyway, so you introduce new variable for all derivatives up to 1 less than the highest order. Okay, so for example, I'm going to call, this is the 0th derivative, right? So this would be u. I'm going to call it u1. Okay, and then I'm going to introduce a new variable, call it u2 for u prime. You don't introduce a variable for u double prime. This is how the setup works. Instead, we're going to take the derivatives of these. Okay? So then from this, you take the derivatives of these guys. So u1 prime becomes u prime. So u1 prime becomes u prime. But what is u prime? It's u2. So there you go. You have your first initial value ODE, du1 by dt equal u2. Right? So that's what we're trying to write the system as. And then the second one, u2 prime, is u double prime. Now we're going to use this over here in a second. Okay? And then finally, you update your initial conditions. You convert your old initial conditions into new initial conditions. So u at 0 equal 1. This becomes u1 at 0 equal 1. Okay? And then u prime at 0 equal to 0. So u prime at 0 equal to 0. This becomes u2 equals 0. We're trying to convert everything into IVPs with u1 and u2. We have the first IVP here, which is u1 prime equal u2. The second IVP is going to be in u2. So we rewrite this original ODE using u1 and u2. So what happens? U double prime is u2 prime. U prime is u2. And u is u1. So now I have 2 new ODEs. u1 prime equal u2. u2 prime is minus 3u2 plus 4u1 plus sine t. And you get this. So U1 describes the displacement, and U2 describes the speed. Okay? So now you have a system of two first order initial value problems. Okay? What's great about this too is that suppose you found a way to solve directly for U numerically for the displacement. And then I ask you about the speed. You have to numerically calculate the speed by computing numerical derivatives, right? Doing it this way, you automatically get the displacement and the speed by solving this system. Okay? This is another example. The oscillations of a pendulum is given by this second order equation. So you see second order, you're going to convert this to a system of two first order initial value problems. You declare theta 1 is theta 2 is theta prime. You take their derivatives. Theta 1 prime is equal to theta prime, which is theta prime is theta 2. You put theta 1 prime is theta 2. That's your first ODE. Your second one, you keep it for a second. Theta 2 prime is theta double prime. We're going to apply this in a second to this guy. And then you update your initial conditions. So theta 0 means theta 1, 0 equal 1. And theta prime at 0 means theta 2 at 0 is equal to 0. And then you take this here. Theta double prime is theta prime 2. And sine theta is sine theta 1. Right? And you get a system of two first order initial value problems. Okay? Another example. We will solve this problem a little later. This is a parachutist in free fall. And another example with a third order ODE. So a third order ODE, you will end up with a system of three first order ODEs. Again, you have to declare a new variable for the zeros derivative, first derivative, and second derivative, not the third one. Okay, so y1, y2, y3, you take their derivatives, you apply the initial conditions, you substitute back, and you get a system of first order ODEs. Remember, solve IVP is solving equations of the form d phi by dt equals something. All of these are d phi by dt equals something, d phi by dt equals something, d phi by dt equal all of this. Okay? Now, the next thing I want to discuss is how we can build systems of so I can solve any one of these systems. Let's actually solve a more interesting system. The next step, the next way to create systems of ODEs or where they arise from is by using some principle of conservation. I like to call it compartment models for ODEs. So this would work for kinetics, and it can work for other things as well. So the way I explain this is, consider a department store that looks like this. And the store has a number of people in it, your shoppers, employees, solicitors, etc. And there's just like a bunch of people in there, a bunch of kids running around, like, crawling everywhere and, doing their thing and screaming, etc. But there's people in the department store, they're walking around. And assume that we have n people in there. That's the total population inside that department store. Okay? So this is an example of how to think about systems of ODEs. So this is classic way of thinking about kinetics and concentration. Okay? So this applies directly to kinetics. Now, the store also has an exit and an entrance. People go in. I mean, when you go to a store, people don't respect which door to go in. Although it says an exit, I always go through the exit for some reason. I'm like waiting for someone to come outside. Okay? And then they remove that sensor from the outside, so you cannot go in through the exit, which is very annoying. But suppose that people just go in and people leave the store. The rate of change of the population n inside the store depends on how many people are entering and how many are leaving, right? That's a simple concept, right? And if people are leaving the store, then we expect the population to decrease. That is, the time rate of change of n is going to be a negative number. Agreed? So whenever you see minus a quantity on the right-hand side, it means you are trying to reduce the rate at which the thing is changing, right? So you are trying to reduce the population. So here, if dn by dt is a negative number, then n is shrinking over time, because we are taking people out of the department store. Obviously, the larger the population in the store, now this could be a fixed number. You could say 1 person, 2 persons leave per minute, if T is in minutes, for example. Okay, or 1 person leaves every minute, that's bad. Maybe 1 person leaves every 10 minutes, or 5 people per minute, or something like that, right? It could be a fixed number. But in general, the larger the population in the store, the more people are likely to step outside. So in other words, what I'm trying to say here, this rate of people leaving out is not a fixed number. It's usually a function of the population inside the store. Okay, so it could be proportional directly to n. Okay, it could be like 5 times n, or like 0.1 times n, or it could be 0.1 times n squared, or square root of n, right? But it will depend on n. In one way or another, it should depend on n. So typically, one way to say it is dn by dt, the rate at which people are leaving, is minus alpha n. Okay, so alpha could be a small number, large number, or alpha could depend on n as well. It doesn't have to be alpha n, could be alpha n cubed, alpha cosine n, but it's a function of n. Okay, so keep an open mind about that. But what I want you to think about is that this is telling us things are leaving this compartment. So if you think of this is where n lives, a negative term on the right-hand side of a differential, of a derivative, means we are consuming the reaction, okay, or people are leaving the store. People are leaving that compartment. By the same token, when people go into the store, okay, when people go inside the store, then we are increasing the population in the store. So the rate of change of population in the store is going to be positive because we're going up. So hence, you see, if you see a positive term on the right-hand side of a first derivative, you are adding to that compartment. You are bringing people in. You are bringing concentration in. So when you think about this in terms of kinetics, chemical reactions, where 2 compounds react, one of them is converting to, they're both converting to another. So you're depleting those 2 and filling in a third compartment. Similar way. Now, the more people, now this rate of people coming in usually doesn't depend on how many people are in. Maybe it could depend. Maybe you could say, oh, there's a lot of people in the store right now, I'm not going to go in, right? So it could be a function of n, but in general, it's a function of how many people are outside. Okay, how much there is outside people wanting to go into the store. And if the outside population is called I, then you would say that dn by dt is beta I. Okay? Some coefficient times the population outside. The larger the population outside, the more people are likely to go in. Nonetheless, in general, the rate of change of the quantity that you're looking at in the compartment is a rate that's coming in minus a rate that's leaving. Very simple. Now, those rates could be complex functions of other things, but you should be able to tell that when it's positive number, then things are coming in. When it's negative, then we are depleting whatever is in there. Okay, so I'm going to use this concept now to develop with you a model for an epidemic. So pay attention here because this is likely going to be on your project to take this model and make it a little bit more complicated. Okay. So I'm going to consider 3 populations, 3 compartments. 3 department stores, okay, 3 compartments. A compartment filled with susceptible people who are just generally not infected, not coughing, don't have the flu or the COVID or the cold or whatever. Okay, and then a compartment of people who are infected, and then a compartment of people who have recovered. And I want to find a way to connect all of these 3 together, because the interaction of a susceptible person with an infected person is going to cause an infection, and then they're going to infect others, but they're also going to get recovered. So there's a balance going on between these 3 compartments. Okay? So people generally move out of susceptible to become infected, and then the rate at which they're moving out is negative, right? Because you're going from susceptible. So that's a fixed population. I have a fixed population. There's nobody coming into susceptible anymore, okay? And we're assuming that once you get infected and recovered, that's it, you have immunity. You're not going to go back to susceptible. Although you might go back to susceptible, but we're assuming not. Okay, so there's no people coming into susceptible. So the only way for the change in the susceptible population, ds by dt, is for people to leave out of susceptible population at a rate minus R1. Okay, now this R1, like I said earlier, we're going to assume it's proportional to the size of the susceptible population. The more people you have, okay, the more likely you're going to get infections versus like a room that has 2 people in it or a room that has 1,000 people in it. There's going to be more likely infections with a larger population. But not only that, the rate of, for a susceptible person to become infected, they have to interact with an infected person. Okay? So you have to interact with an infected person. Mathematically, that is expressed as a product. Okay? So whenever you take 2 reactants, they're interacting with each other, somehow you want them to touch each other, then you express that as a product. Or square root, product of square roots, for example. It's a product of some sorts. So in this case, really, the right way to express this is some coefficient times the number of infected times the number of susceptible. Now remember, these are all in the same room, but I'm dividing them into compartments. We have a total population of 1,000. 2 people are infected, 998 are not infected. When the 2 people start interacting with the susceptible, then they're going to get them infected. And that rate, you're multiplying 2 by 998, that's going to be a large number, versus when you have 2 infected and only 2 susceptible. That's less likely that they're going to interact with each other, right? So that product is a good representation of the interaction between infected and susceptible. They are not separated, so I put them in compartments just to designate them, to tag them, but they're all in the same room or in the same city. Okay? So it also depends on contact with the infected, and we express that as some coefficient times I times S. Okay, so that gives me my first differential equation. Now, I am going to go to infected. There's things coming into infected that's coming from susceptible at this beta coefficient. Remember, I'm taking beta fraction of this, bringing it into here. Okay? And so that's the in, beta IS, because beta IS left the susceptible compartment and entered the infected. Agreed? So I times S times beta is the fraction of the susceptible population that became infected. So it left the susceptible population. Where did it go to? It became infected. So I have beta IS that became infected. Now, after a while, these infected people, they're going to recover. 14 days for COVID, 2 days for the flu, 5 days for the flu, right? There's a rate at which they are being recovered. And suppose that coefficient, that adjustment coefficient, we're going to call that gamma. And the rate at which people are recovering is simply gamma times I. It only depends on time. So it's just a coefficient times the infected. How many people are leaving infected to recover? In epidemiology, this gamma is 1 over how many days to recover. So for COVID, gamma is 1 over 14. For the flu, gamma is 1 over 7. For the cold, gamma is 1 over 10. Okay? It's a real number, and that's what they discover when they develop this model. Okay, so now we have two ODEs here. And with that, I still have 1 term here. And for the recovered, notice that these 2, I can solve them independent of R because they only depend on each other. But R, the amount of people recovered, depends on the infected, how many people are leaving infected. So dr by dt, the rate of change of recovered, has only people coming into it. So it's going to be a positive term as gamma I. Now, when I look at this system, I can immediately tell that susceptible is going to decrease, okay, And recovered is only going to increase over time. But infected has both positive and negative terms, right? So depending on that balance, it might go up and then decrease, or decrease and then go up. Most likely it's going to go up and then decrease, okay? Just by looking at the differential equations. Okay, so apply this not just for epidemics, apply it for when you're looking at chemical kinetics or any balance where you have a system of first order equations. Think of it as compartments. Things are coming in and things are leaving or being depleted. Okay. Now, when you do this, and we're going to solve this together, I showed you this last time. If we're starting with a population of 1,000, let's say, 2 of them are infected, or 1 is infected, and 999 are not infected. And then depending on that interaction and the coefficients beta and gamma. So beta designates how infectious the virus is. Like if somebody talks, are you going to get infected, or do they have to spit in your face for you to get infected? Or cough in your face, okay, sort of better word. Right? Do they have to cough in your face 17 times for you to be infected? Or if you just walk by them, you're going to get infected. So the larger the beta is, the faster the infection rate is going to be. And I can tell from here now, if I change beta, if I increase this beta, this time is going to shrink. I'm going to get people infected much faster. The smaller the beta is, the longer it's going to take for the susceptible to interact with the infected. So thinking about this intuitively. And then over time, we're going to, as the blue shrinks, the susceptible shrinks, the red starts increasing because we're moving people from here to here. And then there's a crossing point, and then we start getting into recovery. It takes about 14 days. See this number here? This is 1/14. At around 14 days, people start recovering. And then like we said earlier, susceptible is only going to decrease, recovery is going to only increase, but then the infected is probably going to increase and then decrease over time. Okay? Now, how do we do this? We're going to use solve IVP, but we will write everything as a vector, as an array, just like we did with root for systems of nonlinear equations. And the nice thing about this, you put everything on the left-hand side, all the derivatives on the left-hand side, ds dt, di dt, dr by dt, and then all the right-hand sides on the right-hand side. And you write this as a vector equation, d by dt of SIR, that's why it's called the SIR model, SIR model, equal to a vector of right-hand sides. And that's exactly what we're going to program. Our right-hand side for solve IVP is going to be these 3 guys. And so in vector form, this is written as a vector of derivatives equal a vector of right-hand sides, and each right-hand side depends on all the other ones. This is a vector right-hand side, and the argument of the right-hand side is also a vector because phi contains Si and R. Okay? We Pythonify this simply with the same way we did with root. We will use solve IVP. So solve IVP solves a system of equations of this form, not just one equation, but a system of equations. Let me fix this actually, because this needs to be t comma phi. Will you just go away? Go away. Okay. So this should be right-hand side, t comma phi. Okay. And essentially, our solution vector that contains the dependent variable is just a vector. We're going to rank them the way we write the system. So if we wrote it as SIR, we're going to put SIR. If you wrote it as RIS or RSI, put it in that order. Okay? Here I'm calling them generically phi 0, phi 1, phi n, and then RHS 0, that's the right-hand side of this equation, right-hand side of that equation, and so on. They need to be consistent with each other. So solve IVP does the same thing, but now the right-hand side is a vector that returns all the right-hand sides of your dependent variables, of your first-order equations. Phi 0 is a vector of initial conditions. Now you need an initial condition for each variable. Okay, we're going to do this for the susceptible, infected, and recovered. So we need initial conditions for susceptible, whatever, 999, and then 1 infected, and then 0 recovered initially. And then the t-span is the same thing. It doesn't change. It's just a tuple of 2 values, t0 and t-final. Okay. So for example, for the SIR epidemic model, we have right-hand side 0 for the S equation, and right-hand side 1 for the I equation, and then right-hand side 2 for the R equation. And phi 0 is S0, I0, and R0, the initial condition for susceptible, infected, and recovered. Okay? And then T0 to T end. Now, when you solve this for a system of equations, you still access the solution from sol.y. But now, sol.y is an array of arrays. It's not a matrix, it's an array of arrays. The first array in the array of arrays is the solution of the first equation at all of those time points. Okay? So phi 0 is your first dependent variable, and the first array contains phi 0 at all the time points that it solved the system as, t0, t1, whatever, to t end. To access this, all of this phi 0, you simply say phi 0 equals sol.y at 0. Give me the first array in this array of arrays. To access the second one is simply phi 1, give me sol.y at 1. So that gives me the second unknown, and so on. Okay, and then you can plot those very nicely. All right. Okay, so let's go ahead and do this in Python. I'm going to write this in this form. I'm normalizing here by the total population size so that I get fractions from 0 to 1 or 0 to 100% of a population. So this is my system of equations. I have S, I, and R, susceptible, infected, recovered, and the right-hand side. So we'll do this in Python together. Let's get a new, fresh Jupyter notebook, and we will play around with this and see what we get. So pay good attention here, because this will be part of your project, okay? All right, so I have to create a new notebook here. I used to create to do file new notebook, and it would just open up one for me. Now it doesn't. It kind of puts it in the directory, so I have to go to the directory, double click on it, and move it over here. Window, move to Quest on. Okay, so let's say fall 2025 SIR model solve IVP. Okay, so we'll get our boilerplate first. And I'm going to put solve IVP at the top. Okay. Let's start the, let me move the slides so we know what we're solving. Always have your math handy so you know what you're actually solving. Where did it go? No, not that one. Oh, good grief. Where is it? I can't find it. Okay, I'm going to try something here. Let me just quit it. Sorry. I should just drag it by hand. Okay. So we're solving this. What I need here, I will first determine I will first set the parameters. So my total population is, let's say, 1,000, 1.0 e to the 3. So 1,000 total population, that's n. And let's say initial, for my initial, let's say first, no, beta. Let's say beta is equal, I don't know, just put some numbers, 0.75. And then gamma is equal 1 over 14. So roughly gamma from all studies I've seen is 1 over the time it takes you to recover. Okay, and that's been very accurate from the experiments I've done with this model. So it's a very accurate representation of what's going on. So we'll think about this as a COVID or, I don't know, a really nasty flu. Okay, initial conditions. I have I0, I have S0. Actually, no, let's do one infected person. And then R0 is 0. So that gives us S0. We need to be conservative. To conserve things, it's going to be N minus I0 minus R0. Agreed? So total population minus infected minus recovered initially is going to give me S0. So this would be 999 in this case. And then T0 equals 0, and T final is equal to, let's say, I don't know, we run it for 500 to 300. Let's see, 100. Let's do 100 or 200 days, 100 days. Okay. So this equation, the dimensions of this are going to be in days. So the rate of change per day, okay, because we're not tracking over minutes, it's meaningless. So all the dimensions are in days. Okay, so these are the initial conditions. Now let's define SIR right-hand side, and we're going to give it T, and we will give it the solution vector. We will call this, let's call it Z. So that's going to be, this Z is going to be the vector of S, I, and R. Okay? And then I want to pass, actually I'm not going to pass parameters right here. Just keep it simple like this. And then the first thing you want to do is pull out S, you could say, is Z0, I is Z1, and R is Z2, right? So don't worry about how this works out. I know that I'm solving 3 equations. So solve IVP is going to return to me a vector of containing these variables, these 3 variables. And they're going to be stored in an order of my choice. And I'm choosing to put them in this order. The initial conditions are also going to be S0, I0, R0. So everything is going to go SIR. They're going to be SIR like this. Another way to do this is to do S, I, R equals Z. Okay, so both of these are valid. So now I have access to S, I, and R, and then simply I can say RHS1 is ds by dt. This is ds by dt. That's minus beta over n times I times S. Right? So that's ds by dt, right? So that's this guy, minus beta over n times I times S. RHS2 is beta over n times I times S minus gamma times I. So this would be di by dt. That's the right-hand side. And RHS3 is simply gamma times I, and that would be dr by dt, correct? And then we will return just an array of RHS1, RHS2, RHS3. However you want to name them, I would have really named them ds dt, di dt, dr dt, because that's just the right-hand side. But you can name them this way, and that works just fine. Okay? Finally, my initial condition is going to be S0, I0, R0. And I'm declaring that over here just that it's easier. And then solution is solve IVP. And we're going to give it the SIR right-hand side. and we will give it T span equal T0 to T final, and we will give it Y0 is equal my initial condition. Okay, let's force it to solve it at a specific set of points. So I'm going to use T eval here in this case. Time points is equal mp.lin space. I want it to be nice and smooth from T0 to T final, and I'm going to put 500 points, so just get a quick solution. And then we will put T eval here is equal to time points. Okay, I'll give you a second to catch up. Okay, sorry. Anyone still working? Yes? Nobody's? Okay, great. So now we have our solution. Let's run it. Yay, no error. Good. Okay, so now I just want to plot. Okay, so I want to plot S, I, and R all on the same plot. So I know so if you look at sol.y, it's going to be a huge array of arrays. So notice, it's when you see two brackets, you know there's an outer array and a bunch of inner arrays. So this first set is S, contains the susceptible. And look, it starts at 999. Isn't that cool? This second set is the infected, and it starts indeed at 1. So you see it in another bracket, and then closed over here. There's 3 points here because there's 500 points. And then the recovered, starting at 0, and then all the way to the end. Okay? So let's pull those out. And I know I told you here we can do it by doing phi0 equals sol.y0, phi1 equals sol.y1. Or another way to do it is phi0, comma phi1, comma whatever equals sol.y. So that's a much faster way. So I'm going to put SIR equals sol.y. And for t, for the plotting, I'm going to put sol.t. Okay, now I can plot. Let's see, plt.plot. I'm going to put plot S. I'm going to divide it by n to normalize it so I don't start. Well, let's keep it as is. Okay, and then let's make it blue. Those are the susceptible people. And then label equal susceptible. Plt.plot time points, and we're going to do I, and we're going to put this in red. These are the infected, and label is equal infected. We always put the infected in red. Let's make the lines a little bit wider. So line width is 2, LW is 2. And last one, plt.plot, again for my time points, and this would be the recovered, and this is going to be in green. Line width also 2, and label is equal recovered with immunity. Okay, and then, look at that, beautiful. plt.grid, yes. Did you get that? Yeah? Then you can put your labels, plt.x label, days, since patient 0, just days. plt, I don't want patient 0 to feel bad. Label, number of population, just population or number of people, okay, and plt dot legend. Let's put the legend on it. Okay. Look at that. Very nice. As expected. You have a tool now in your hands to start exploring what happens when we change beta and gamma. And those are really the only two parameters that you have over here. We said beta is connected with how infectious the disease is. So we expect that for larger beta, okay. What do you expect to see for larger beta? Just from the plot here. And let me shrink the plot a little bit. So PLT dot X limit, we're going to do from 0 to, let's say, 40 days. Okay, so you can see this a little bit better. Okay. So what do you expect if beta is large or beta is small? What do you expect to see?
Beta is the rate of transmission of the disease, right? So
Or how infectious yeah, it's related to the rate, or specifically how if it's very infectious, it means like in
will rapidly drop in susceptible and rapidly increase in infected.
okay. So instead of having this curve, it would be a rapid drop here, right? And then the red would be a rapid rise. And if beta is small, it's going to take a long time for this to drop. Okay, so let's test this. This is a hypothesis. Okay, let's test it. We're going to test it with our code. Yay. Okay, large beta. Let's do 1.75. I don't know how large we can go, but we'll try it. Okay, look at that. It did drop rapidly. Initially, it was, okay, so let's go to where we had it initially, 0.75. Okay, so I'm going to keep this here. Okay, so that's the initial. Approximately the drop started at 5 days, where we started seeing infections from susceptible. So let's increase this beta. Let's put it 10.75. And look at that. It's just like this insane drop very quickly. Within half a day, maybe, you start seeing infections, right? Because it's a very infectious disease. Now, on the flip side, if beta was very small, you will see a long, oh, look at that. Nothing is going on for a while. So let's make it 0.1 instead. It's still going to be a long while before you start seeing infections. Let's make it 0.3. Okay, so it takes about, what, 15 days, 10 days to 15 days to start seeing infections occurring. Okay, so that's what beta is doing, is the rate is connected to the rate of making susceptible people infected. Okay, so let's put 0.75. So those numbers I took actually when I studied this during COVID. Epidemiologists were trying to estimate those numbers. So they will try to fit this model to observe data. And those were actual numbers that were reported in some of the literature. Next is gamma. So let's run this again here. So that's what's annoying with not passing arguments. I have to go back and edit this and run it all over again. I should have passed these arguments here in the SIR right-hand side, which you will do in your project. So then I would just change it over here, not up there. OK, so let's run this again. This is where we started with. Now, what happens when gamma is small or large? And again, every time you're thinking about a system, take the extremes. What happens when the parameter is very small? What happens when the parameter is very large? I said that gamma is related to the recovery rate, right? So if you look here at minus gamma I, this is pulling people from infected into recovered. So it has to do with the recovery rate. Okay, it has to do with the recovery rate. Roughly from what I understand, recovery is about 1 over, well, not in this case. It's 1 over the number of days. It's related to that. So what happens, let's just forget about that. Let's just think what happens when gamma is small and gamma is large. When gamma is small, what do you think is going to happen? When gamma is small,
a slower recovery rate, so your infection or your amount of infection isn't going to like inflect as fast.
Okay.
And if it's small enough, you'll like max out where everybody's infected.
And
then
they
actually
recover.
levels.
Yeah. Yeah, when everybody is infected. Okay, so let's see that. So we had two opposing hypotheses. As you said, when gamma is small, we're going to see a faster recovery. And you said when gamma is small, we're going to see a slower recovery. Agreed? Okay. Do you want to take a vote? This is not science is not a democracy, but like I'd love to kind of see your opinions on this, hear your opinions. Who do you think is right? Okay. We got one vote, 2 votes for Isaac. Okay. Everybody else is abstaining. You're throwing your vote away. You're throwing your vote away. Okay, gamma. So what is 1 over 14? So let's just print gamma right now. Okay, 0.07. So let's make gamma bigger, 1. Okay. So initially we were about here, what, 7.5 days for the first to start picking up on recovery. So now we increased oh, look at that. We increased gamma, and it pushed everything way out. We can't even see anything anymore. So that was pretty big change. So let's see 0.5. Okay, so when we increased gamma, it took longer to recover. It took longer to recover, right? So we started picking up this around 10 days, okay? And so let's increase it to 0.75, or let's decrease it to 0.25. And as you decrease gamma, actually, you're seeing, so you were right, you're seeing quicker recovery. So everybody who voted with Isaac, get out of here. No. And that's counterintuitive, right? Because you're thinking that this is a ratio that you're multiplying. You should be increasing the rate at which you are depleting I. The problem is that there's this interaction here between how many people are coming into I and how many are leaving, right? Because there's this parameter here that's also influencing what's happening with gamma I. Because if you have little i's, small number of I, then you have to make gamma very large to pull out enough people into the recovery, right? Does that make sense? So it's because of the presence of beta IS that this is going on. Now, what would be interesting is to vary them together. If beta is large, what happens to gamma small and large? And if beta is small, what happens to gamma small and large? Which you will explore proudly in your project, okay? And present that to me, okay? But yeah, those are the things you can ask, right? When you have a model that you can run and play with and understand. So in your project, what I'm thinking I will ask you to do, let me see. What I will ask you to do, let me hide this so you don't see the secret, the secret answer. Yeah, so what you will do is you will add a compartment of distanced people. Okay? So I want to study the effect of social distancing. Does it make a difference on the red curve or not? And you'll put a category of socially distanced people that only communicate with susceptible. So you either social distance yourself or not. If you're infected, you're assumed, you're in the hospital or something, right? You're not, or you're just running around, I guess, keep running around. But you'll add a socially distanced people, go infect people, develop population immunity. So you'll add a compartment. So let me show you this slide. And I call it the third model. What is it? It's right here, okay? So roughly that's what I'm thinking for your project too. So you'll add a distanced population, and there's a rate at which people come from susceptible to distanced or move from distanced to susceptible. And those delta 1 and delta 2 I will ask you to figure out a way to say, okay, my hospital, my number of infected people is, once it reaches a certain threshold, start distancing people. And then when it's below a certain threshold, start getting people back into business. Right? So you're going to see an oscillatory behavior in the system. You'll have like a condition to say when my number of infected people reaches capacity. So if you go back here, again, this is what people were worried about during the pandemic, is when we reach peak, we don't want this to be above hospital carrying capacity. Hospitals, when they plan for the flu season, they're not going to make 3,000 beds. They have like 300 beds because they assume, on average, people will never hit that capacity. And so that was the problem during the pandemic. Everybody was getting infected so quickly. And so the question is, well, okay, instead of locking everyone out, how about we track this? And then when it reaches, let's say, 100, trigger social distancing. People, go stay home. And then until you start seeing this decrease, and then once you hit 50, for example, then people start going back into normal life. So you're going to see this oscillatory behavior until everybody is recovered, essentially. So it's like an engineer's perspective on dealing with all the pandemic fiasco and what people were fighting about. We can solve this with some math and some common sense, right? So that's what you will do in your project, I think. Okay, I think that's what you will do in the project. Okay, and this is still within chemical engineering. So we deal with this is a system of ODEs similar to reaction kinetics, and it's not this. I mean, we did a project here in chemical engineering for the Utah Symphony. So you can look us up on NPR or what is it? The KSL no, not the KSL radio. No, KUER, yeah, NPR Utah, right? Yeah, so you can look us up for the study we did for the Utah Symphony, for the COVID spread in the Utah Symphony. So it's still within our purview. We can do it all right? I'll let you go. Godspeed, have a nice weekend. We'll see you on Tuesday.